Pluto is a faraway and perplexing little planet that was once a singular individual from our planetary family. Anyway, late terrifying announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have carried Pluto back into the spotlight with a staggering exposure. They suggest that this chilly world is on a potential collision course with Neptune. Yet, how should this happen, and what might be the results of such an enormous event? Are we seeing an intriguing, grandiose characteristic, or is there something else to this coming pompous collision? Join us as we examine the possible results of a Pluto-Neptune impact. Pluto, a past planet that was minimized to a dwarf planet, partly due to its flighty orbit, remains a subject of intrigue and focus in the astronomical community. According to recent estimates by leading scientists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about an expected hazardous collision between these two planets that could pose a gigantic risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It requires a staggering 248 years to complete one orbit. This means that since its discovery in 1930, it hasn't even finished one full revolution. Yet, the intrigue doesn't stop there. Pluto's orbit is marked by its significantly bended shape, drifting off considerably from the almost circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, set at 17 degrees to the ecliptic plane. The path Pluto follows is much more tilted compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. Arguably, one of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's. For at least 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we would expect from their positions in the solar system. This leads to the inevitable question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out due to its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit, amid these complexities, is a testament to the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects, like Pluto, Neptune, and the Sun, move and interact with each other through gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. For Pluto, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms alpha libration and extension libration, along with the VZK oscillation, are part of this puzzle, as demonstrated by astrophysicists. What keeps all planets in their orbits is a phenomenon called alpha libration. Relative to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from influencing each other. Extension libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another critical aspect in this situation is the VZK oscillation, named after three scientists, von Zipper, Leo, and Kai, who studied how objects move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pull impacts how they move. For Pluto's case, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Despite its orbit seeming chaotic, this oscillation helps keep it moving smoothly. The VZK oscillation shows that even if things in space appear wild and irregular, certain patterns and rules maintain a level of control. These factors help stabilize Pluto's orbit, ensuring that it doesn't crash into Neptune or lose its path. The three-body problem helps us understand how these orbits change based on how these space objects pull on each other. Focusing on this helps us learn more about Pluto, our solar system, and distant stars and their worlds. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is, in fact, tumultuous. Minor deviations in initial conditions lead to enormous differences over millennia. Nevertheless, these fascinating properties of Pluto's orbit have been found to maintain stability over extremely long timescales, effectively holding chaos in check. Recent observational advances have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet influencing things. Jupiter's gravity also plays a huge role in stabilizing Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady course for a long time, perhaps even billions of years. So, it seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These phenomena are vital for the universe's functioning, maintaining the control and stability of celestial motions. Without these forces, the solar system, as we know it, would be a much more chaotic and inconsistent place. Bodies like Pluto might collide with others or be thrown out of their stable orbits, causing cascading effects on other celestial bodies. For Pluto, especially with discussions about it possibly crashing into Neptune in the future, understanding its orbit is crucial. This provides us with a clearer picture of the dynamic nature of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of harmony through the complex exchange of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependency of a celestial body's orbit on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can dramatically alter its long-term path within the vast expanse of our solar system. Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to major discoveries about its composition and behavior. One of the most fascinating features of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided stunning data about this distant world. The outer layer of Pluto is characterized by vast plains, towering mountains, and deep valleys. One of the most striking features is the Sputnik planitia, a massive heart-shaped plain primarily made of nitrogen ice. This region showcases a diverse array of landforms, including large ice sheets and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active, despite its vast distance from the Sun and frigid temperatures. Another intriguing aspect of Pluto is its atmosphere, predominantly made up of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is volatile but exhibits fascinating seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This unique behavior is a reflection of the intricate relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The relationship between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space between them, rather than Pluto simply rotating around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, offering scientists a glimpse into its formation. Pluto's orbital characteristics could provide insights into the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a crucial role in shaping their current orbits. One of the key implications of understanding Pluto's orbital characteristics is the potential impact on our understanding of the local solar system's dynamics. Understanding Pluto's orbit also has broader implications for how we view the stability of the entire solar system. The intricate relationships between the planets and dwarf planets, as well as their gravitational interactions, help to maintain the system's equilibrium. These gravitational dynamics not only determine the paths of planets and smaller bodies, but they also influence the overall architecture of our solar system, ensuring that objects like Pluto remain in stable orbits despite the apparent chaos. The role of large planets like Jupiter and Saturn in maintaining this stability cannot be overstated. Jupiter, in particular, acts as a gravitational shield for the inner planets, including Earth, by deflecting potential impactors from the outer solar system. Its influence extends to the Kuiper Belt and beyond, providing a stabilizing effect on the orbits of objects like Pluto. Saturn also contributes by influencing the orbital characteristics of objects in the Kuiper Belt, ensuring that their trajectories remain consistent over time. These interactions between the outer planets and objects in the Kuiper Belt suggest that the solar system's current configuration may be the result of billions of years of gravitational tuning. The present-day arrangement of planets and dwarf planets, with their specific orbital patterns, may be the product of complex gravitational forces that have shaped the solar system over long periods of time. For Pluto, understanding its orbit and interactions with Neptune is crucial not only for understanding its own fate, but also for gaining insight into the early history of the solar system. The Kuiper Belt, where Pluto resides, is a remnant of the solar system's formative years, containing objects that have remained relatively unchanged since the system's birth. By studying Pluto and other Kuiper Belt objects, scientists can learn more about the conditions that prevailed in the early solar system, as well as the processes that led to the formation of the planets and other bodies. Pluto's unique orbital behavior also highlights the importance of studying smaller, distant objects in our solar system. While the major planets have been well studied for centuries, the outer reaches of the solar system, where Pluto resides, are still relatively unexplored. The discovery of new objects in the Kuiper Belt, along with missions like New Horizons, has opened up a new frontier for scientific discovery. As we learn more about the characteristics and behaviors of these distant objects, we can gain a deeper understanding of the forces that govern the entire solar system. In conclusion, the story of Pluto is much more than the tale of a distant, icy world. It is a story of how gravity, time, and the complex interactions between celestial bodies shape the orbits and paths of the objects in our solar system. Pluto's unusual orbit, its relationship with Neptune, and its interactions with the other planets demonstrate the intricacies of celestial mechanics and the ongoing evolution of our understanding of the universe. As we continue to study Pluto, the Kuiper Belt, and the other distant regions of the solar system, we may uncover even more surprising details about the forces that govern the motion of the planets and the history of our solar system. These discoveries will not only deepen our understanding of Pluto itself, but will also shed light on the broader workings of our cosmic neighborhood and our place within it.